Today I will introduce solar energy, and we will start our final chapter, which is economical analysis. So basically today we will be done with the material. Just we need one extra session to do a makeup for the session we lost in order to do some practice on some problems. Okay. So here in the previous presentation your friends have done, we have talked about solar energy, and here we will see several types of systems using solar energy. So to start with, solar energy offers many advantages over other conventional energy sources. So first, it's free because we can use it for example, anytime, especially in sunny regions, okay, and we don't have any cost, so we can just use the energy of the sun, and we just need to take into account the cost of the system initially. To implement the system, we have a certain initial cost, and we have some maintenance cost with time, but after other than this we don't have to pay anything. So this is why the payback time period of solar systems is in general short, okay, which makes solar energy very important and presenting a very high potential. So the other advantage of solar energy is it's that it's available everywhere and inexhaustible. And of course, it's a clean source. We don't have greenhouse gases emissions. We don't have risky pollutants. So it will reduce the demand for fossil fuels and hydroelectricity and their environmental drawbacks. In addition, it can be building integrated, which can reduce the energy distribution needs. So no need to have, if you want, a very large distributing system. So it's local. So we put the system near the house, and we can benefit from the solar energy. Now, if you remember in chapter 2, we have already seen that the solar constant is very high. It's nearly 1,350 watt per meter square. And if you remember in one of the problems of chapter 2, we demonstrated together how we get this constant. The sun emits energy as electromagnetic radiation, and we have seen that we have a very large spectrum of waves. And the energy of the sun is equivalent to 5,725 degrees furnace, which is a very high temperature. And it produces 36,000 times the amount of energy that is provided by the total world oil consumption nowadays. Now, for solar energy can reach the Earth in several ways, as direct, reflected, or diffuse radiation. First, when we talk about direct radiation, it is energy that is coming perpendicular to the surface. Okay, so when we talk about direct radiation, we have the energy that is directly, we get it directly at the Earth's level, so it will reach the Earth directly. Okay, and it can reach it in an inclined way, or it can reach it in a perpendicular way, but the most efficient way is the perpendicular one, because when we have the sun directly hitting perpendicularly to the surface, this will be the maximum flux, okay, that can be absorbed in this case. Now, concerning diffuse radiation, it is the energy from the sun that is scattered within the atmosphere by clouds, dust, or pollution and becomes non-directional. What we mean by this is that it will not reach directly the Earth. It will be obstructed by something as clouds or dust or pollution, and then it will be redistributed, if you want, in all directions. So it will not be directional anymore. This will reduce sometimes its strength, but it will be in this way distributed to a larger area. Now, on a cloudy day, sometimes we can have 100% of the energy transmitted by diffuse radiation, because if you have a lot of clouds, so no percentage will be able to reach directly the Earth. And in this case, we say that 100% is diffuse radiation. In other cases, we have a mixture between direct and diffuse radiation. This is almost the case, because in general, it's rare to have 100% direct radiation, because always you will have some obstacles. If not clouds, you have pollution or dust, etc. And the amount of the sun's energy reaching the surface of the earth also depends on cloud cover, air pollution, location, and of course the time of the year, the season. So if we are in winter, not of course the intensity is not like in summer, etc. Now, when we build a solar thermal system, the system should be divided into three parts. We have it part for collection of the energy, we have a part to store the energy, and we have a part to distribute the energy. Okay? So, as for example, if we consider a passive solar building, natural energy will flow through air and materials in using several methods of heat transfer as radiation, conduction, and a natural convection. In this simple example, what are the collectors, for example? If you have a home, windows are the collector because they will allow to absorb the energy of the sun and transmit it to the internal space. Okay, so this energy will be stored by interior materials, and we call this thermal storage. Okay, so if you have heavy materials in your building, they can store this energy, especially when it's not needed. So in during the day, nearly you have a warm environment, so solar energy in excess can be stored in the thermal storage materials. And then during night, for example, when the indoor air is relatively cold, then the thermal mass will restore the heat to keep a comfortable temperature in the space. Okay. Now, water or air solar heaters are in general used natural convection uh, to heat our space and will not require pumps or fans. Okay, so in general, we rely in some systems of water or air solar heaters. We rely just on buoyancy effects because you know that from chapter 2, when we studied convection, we said that convection is mainly due to difference in density of the fluid. Okay, so if you increase the temperature, what will happen is that the density will be reduced. So if you have a if you have a system where water circulates or air, if you heat air, what will happen, or water, then the density will be reduced, and this will lead to upward motion. Okay, in this case, we don't need a pump to circulate our fluid. This is why we say that it's a passive system. When we say a passive system, this means I don't need any auxiliary equipment that need oil or electricity to function. Okay, so here it's completely free because I'm relying on solar energy to produce buoyancy effects that will lead to circulation of my fluid in my system. Now, in general, this can work, but to sometimes if we have to distribute over very long distances, okay, then we can use an active solar system. When we say active, this means that I need to implement a mechanical equipment that will help me into the distribution of my energy, like the pump. Okay, so I can put a pump that can circulate water, for example, in my system to ensure that the circulation will not stop if, for example, I have a reduction of solar energy or something. Okay, so it depends on the size of the system and it depends on the availability of solar energy to decide if I can use a completely passive system, or I need an active system that will use mechanical equipment to be on the safe side when energy is not enough. So an active solar system will use mechanical equipment to collect, store, and distribute the sun's heat. Active systems consist of solar collectors, a storage medium, and a distribution system. Active solar systems are commonly used for water heating, space conditioning, production of electricity, and process heat. Now, when we talk about hybrid power systems, it means that we have systems combining several modes of energy systems. So we can combine a solar system with a fuel system. And this is a very good strategy because sometimes we have sun, but sun and solar energy is not enough for the total demand. Okay, so what we can do when we combine this system with another one, let's say a fuel system, we can reduce fuel consumption when solar energy is available, and when solar energy is not enough, then we put the fuel system on. And in this way, we can ensure a stable delivery of energy. Now, this is a graph for an active solar system. As you can see, the main components are the pump, which will circulate the fluid. So here, let me, okay. You have here the pump. The pump will circulate the fluid in my system. So for example, here, let's say I'm pumping water. Water will go through a loop. Okay, first it will go through the collector. The collector is the equipment that will collect the energy of the sun. As its name indicates, it will collect energy from the sun and will provide it to water. Therefore, water, when going through the collector, will be heated. And then to benefit from this heat, I will take water into a heat exchanger. In the heat exchanger, I have two possibilities. If I don't need now the solar energy, I can use a certain medium to store energy by taking it from the circulating water. Or if I am in the need of water that is cooled, for example, I can circulate here in the heat exchanger another fluid, for example, water, domestic water that is needed in the house. So I can circulate it in the heat exchanger to be heated by my water loop that is going towards the collector. Okay, and then the cycle will be repeated in order to repeat the same procedure again and again. So because when the water here will go through the heat exchanger, it will lose heat to the other fluid. So now it should be pumped again to the collector to be heated by the sun, and then it can go back again for in the heat exchanger to deliver the heat store.
Yes, I have a question regarding this part.
Yes.
We are working on this part on our design of thermal system project. كتير similar to this part with the collector. Yeah. The idea is إنه we are having the collector and the storage tank at the same ground level, at the same level, horizontal level. Yeah. So we only need a pump to extract the water from the storage tank. Yeah. And to pump it into the collector, but we don't need any other pump in order to in order to bring the water from the collector back to the storage tank, right?
Yes, no, from the collector back to no, one pump, of course. Once you give it the energy, you will give enough energy to go over the loop. Okay.
Okay.
You will give enough energy to do the whole path.
Okay.
You know that, I don't know if you are a mechanical engineer, you have taken fluid course. In the fluid course, for example, what you do, you calculate the total losses associated with the whole path, and then you can determine what is the power needed by your pump.
Yes, we're working on this now. Okay, thank you, Miss.
Okay. Now we have several types of solar collectors, and we will discuss several configurations and see the application of each one. So for a solar thermal system, we will have direct conversion of the electromagnetic radiation from the sun into heat through solar thermal collector. So this is the main purpose of the collector, is to take the energy of the sun in the electromagnetic form and transform it to a heat energy, because by passing a fluid through the collector. Solar thermal energy is used especially in colder climates to provide additional space and water heating for domestic and commercial buildings by mounting solar panels on sun-facing surfaces. Now, in this figure, you see two types of solar collector, and we will discuss in more details after each type. But here, the main difference is, as you can see here, for this example here, what are the elements? So you have, in general, we use a glazing cover. The purpose of the glazing cover is if you want to collect better the energy, and then if you want to create like a closed space here so that to reduce the loss of heat by convection. Because if you don't put the glazing, then your ducts will be directly exposed to air, and you know that from convection you can lose heat. By passing air over your ducts, you can have loss of heat from your ducts towards air, which will reduce the efficiency. This is why, in general, putting a glazing here will create, if you want, like an enclosed space here. So the energy collected will be instead of losing some part of it, will be more efficiently used, and it will be absorbed by these ducts in which fluid is circulating. Okay, and in general, we put a thermal insulation on the back also to reduce the loss to the environment. Now, a more efficient design is the concentric tubes. So as you can see here, what we do, we put first also a glass tube from outside instead of the glazing cover. Okay, so it will be in the form also of a duct, and in this way, if you want, what we do, we put the glazing from the two sides because it's a duct, and it's circular, and we create a certain vacuum between the glass tube and the tube in which the fluid is circulating. Why? Because if you create vacuum, you can reduce the heat loss by convection. So this is also a more advanced configuration because the losses are reduced a lot. So, and in both cases, heat will be absorbed by pipe and will evaporate due to. So if you absorb a very large amount of heat, this can lead to change of phase from water to a certain to vapor, if you want. Okay, and in case the heat is not enough to evaporate, the water will remain in the water state, but it will be at higher temperature. Okay, but in general, when we use the concentrated the evacuated tube collector, which is a very efficient type, we can reach very high temperatures. This is why we can transform from water to vapor, and then due to this effect, because you have the vapor phase due to buoyancy effect, this will lead to the rise of vapor in your system, because as it is heated, the density will be reduced, which will allow it to move under the effect of buoyancy. And in this way, after it will go to be distributed, let's say, to a certain system, when it will be cooled, then it will return into the liquid phase, and due to the transformation into liquid phase, it will fall again into the tube. So if you want here, buoyancy effects will allow circulation of your fluid. Now we will see each type in detail. Okay, so the first type is unglazed collector. So as you can see in the figure, it's a very simple design and very simple to install. It only consists of tubes. So you have tubes, and you circulate. You put these tubes on the roof, on the roof, or on a facade that is exposed to the sun, and you circulate water inside these tubes. And due to the exposure to sun, water will be heated. So as you can see here, this is very used for swimming pools, to heat swimming pools, because you know that in summer solar energy is widely available, and the temperature to which you need to heat is not very large because you just want to use it for swimming pools. So this simple system can be used in this case. It has a 3-year to 6-year payback period, which is relatively short. It's good. When we say payback period, it is the time needed for the system to, if you want to compensate for the initial cost, because not only for the initial cost, for all costs until this time. And if you say if you say I have a 3 years payback period, this means that all costs you have put for the installation and for the maintenance until 3 years will be all, you will have gains equal to these inputs. And from now on, and after 3 years, you will start to gain money. Okay, so here, as you can see, you have a distributing system. So here also you can have a pump. Okay, you can have a pump that will circulate water. So first, cool water, as you can see in the blue color, cool water will circulate into the panels, and when going through the panels, it will be heated by solar energy. Therefore, the temperature of water will increase. So when it will go back here to the pool, it will be heated. And now you can extract, and this can operate in a continuous way. You can extract water again from a reservoir, and you can pass it through the panels to be heated to maintain a constant temperature of your swimming pool. Now, the amount of heat delivered by such system is between 2 to 2.4 kilowatt hour per meter square per day, which is relatively, it's considered a energy, but it's acceptable depending on the application. So for heating swimming pool, it's very good, and it represents several advantages due to simplicity of design, etc. But as we said here, we cannot reach very high outputs because we have losses due to convection effects. So if we need more energy to be produced, we should go to other systems. A better system is the glazed flat plate collector. So mainly here, the main difference is that we are putting a glazing above the tubes. This will help in, if you want, reducing a lot the convection losses, okay, because you have that heat that is collected is being stored in a small enclosure between the two, and you have a small air gap between the glazing and the tubes, so convection will be reduced in this way. And the mode of operation is the same. So you circulate, this is the inlet, let's say, you circulate water through the tubes. And when circulating through the tubes, the solar energy collected through the glazing and transmitted to the system will heat the water, and then the water can be used for any application. Like for here, for example, the system is used a lot for domestic hot water, so it can satisfy demands of a home in hot water. And of course, we have the bottom plate for insulation to reduce the convection losses from the other side. And this design is an example of a typical liquid-cooled collector. Air-cooled collector design will vary accordingly, so you can circulate or air or water as fluid. Now, the third type, which is the most efficient one, is the evacuated tubes. So this is the most efficient design, but also it has a higher cost. So as you can see here, you have concentric tubes. The outer one is a glass tube in order to collect the energy from the sun. And you have an inner glass tube, and between them, you create a vacuum space in order to reduce the convective losses. Okay, and you have a fluid tube where we have circulation of the fluid to be heated. Now we will summarize the advantages of each type. Okay, so first, the unglazed collector. It's typically used, as we said, for swimming pools. It represents the advantages of low cost, and it is very efficient at low temperature differences. So if we just want to heat, let's say, to maybe from 24 degrees, let's say, to 30 degrees. Okay, so the amount of temperature we need to heat for swimming pool is not high. In this way, this system will be very efficient. The disadvantage of such system is that it's not good for freezing temperatures because you have a high risk of freezing water. And the capital cost is relatively low due to simple installation, and it's a simple system. So nearly the cost is $150 to $350 per meter square. This is one of the best advantages because the cost is very low. But on the other hand, the energy delivery is also not very high. So it's around 210 to 250 kilowatt hour per meter square, and it's typically used in summer because we don't use it in winter due to the freezing issue. Now, the other type is the glazed collector. It's typically used for domestic hot water needs, so to heat water for a shower or to use water in home hot water. It is also relatively economical with respect if we compare it with evacuated tubes. And also the same disadvantage, it needs protection from freezing during cool seasons. And for the capital cost, it's larger than unglazed, so you can see the difference. It's 450 to 750, but it's still acceptable. And compared to evacuated tube, it's less cost. And the energy delivery is higher than unglazed, so it can reach 500 to 600 kilowatt hour per meter square. Now, for evacuated tube, it's the most efficient one, especially for very large temperatures. Okay, so it will be used when we need to heat a lot. We have a large gradient of temperatures, and it is also used for domestic hot water systems, and mainly in cool seasons. It will be efficient in cool seasons. It provides hotter water, so if we need, sometimes for a shower, for the water used in shower, we should heat it first to a very, very high temperature to kill, because it's advised to kill some bacteria to heat to a very high temperature. And after, when we use it, we can mix this water with cold one. So for these applications, we can use evacuated tube. Now, concerning the disadvantage, it's relatively expensive compared to the other types. So we will not use it in any application. We should use it only in applications where very hot temperatures are needed. And also another disadvantage, like the other two types, that it needs protection from freezing. So what we can do, we can circulate a refrigerant with water that will protect from freezing by lowering the solidification point. Now, for the capital cost, is the higher capital cost among the three. It's between $1,100 per meter square to $1,500 per meter square. And on the other hand, it's true that it has a high cost, but on the other hand, it provides a very high amount of energy, much higher than the two other types, between 800 and 840 kilowatt hour per meter square. Now, each type is good for a certain application. So in general, depending on what is our application, we choose the corresponding type. For example, if you look at this graph represents, I will zoom a little bit. So are you seeing the graph, or it seems that it is
no, yes, I can see.
Yeah, I will, it's better like this. Okay, just 1 second, guys, please. Okay, so here, are you hearing me?
Yes.
Yes, doctor.
Okay, but maybe, are you seeing the PowerPoint? Because I'm not seeing that that it's shared with you. You are seeing
We
now
can
the
see it. Yes.
Yes, we can.
Okay, but I don't have the annotation tool, Zella. Let me check. Okay. Okay, so here in this graph, you have the efficiency of the three types variation with temperature. Okay, if you look at zones of low temperature, and if you are working at relatively low temperature in this zone between 0 and 20 degrees, you can see that the most efficient type is the unglazed one, which is in yellow here, if you see it here. Okay, so here. This is this yellow part, this graph, this one is for the unglazed type. Okay, so as you can see between the three curves, for small temperatures, the most efficient one is the unglazed, because as we have seen together, we have that we need just to increase the temperature by a small amount, like for the swimming pool. So at small temperature, this type will present the best efficiency among the three. On the other hand, as the temperature increases, you can see that we have a decrease in performance of the unglazed type. So we have a large drop of efficiency with temperature. This is why we say that it's not advised to use the unglazed type for large, when we need to heat a lot the fluid. Okay. Now, for intermediate temperatures, so when you exceed 20 degrees, the most efficient type is the evacuated tube ones. But because the cost of this type is high, because it represents a high cost, if the temperature needed to reach is relatively intermediate, not very high, you can go for the glazed type, because as you can see, for the glazed type, you have a good efficiency and at the same time an acceptable cost. Now, in the third region, where you have a very large temperature to reach, you can see that if we increase a lot the temperature, also the glazed efficiency will be decreased in the third zone. So for the third zone, the best option to use is the evacuated tube. So from this graph, we can deduce that for low temperature, the best type is the unglazed one. For intermediate temperature, to make a compromise between cost and efficiency, we can go to glaze type. And for very high temperature, then because the efficiency is reduced a lot for glaze type, then we go to evacuated tube. Okay. Any question on this? Okay. Now, in this slide, we see the example of how we can use a solar system for domestic hot water demands. Okay, so here we have several systems. We can work on thermosiphon block, which rely on buoyancy effects to circulate water. So as you can see here, the design is very simple. What you have is that when your water goes through the collector, it will be heated, and due to buoyancy effects, density is reduced when heated. So due to buoyancy effects, air can circulate, water can circulate upward without the need of any pump. So when you have relatively small elevations, and if you have a small home and you don't have very high heights, and it's not a building of more and 6 floors, it's just 1 or 2 floors, then you can rely on buoyancy to distribute to circulate your fluid. No need for a pump. Okay, so here such systems can work for relatively small height buildings, and no need to put a pump. On the other hand, if you have the height is very large, then you need a pump to circulate your water. And as we can see here, as we described before, the pump will circulate water upward towards the collector. Once passing through the collector, water will be heated. And now, as you can see here, you have in the heat exchanger, you have several possibilities. Sometimes, let's say now you don't need hot water. If you don't need it now, what you can do, you can close this valve, this one. You have 3 valves here. As you can see here, you have 3 valves. If you close this one, then your water will not circulate, because this means that I don't need solar energy, and if you want, there is no solar energy now is not available. And during the night you will shut down your system. During night, no need to circulate your water. So you close this valve and you shut down your pump. During the day, you have 2 options. If you need now hot water, what you will do is that you will open this valve and you will open the second one here. Why? Because if you open this valve, then hot water that is heated inside the heat exchanger will go through directly to your house. Okay, so you can see here that it's directly distributed for shower application, for hot water needs. On the other hand, if you don't need it now, what you will do, we will shut this valve. So this valve will be off, okay? And we will open the other valve here. We open this one. Why we open it? Because we can store hot water now. So this valve will take water into a reservoir for extra energy. So we will store hot water in our reservoir. And then when we need hot water, when it's needed, you can use it or from the reservoir or directly from the sun. Okay, but the reservoir is very important because during the night you don't have the solar energy, so you can benefit from the energy stored in your reservoir to supply hot water. Now, a very important application also in domestic hot water is the floor heating. So you can heat your floor, you can heat your walls also. You can heat your building envelope to ensure a temperature inside your space that is comfortable. Okay, and floor heating is widely used and is very efficient because the floor heating will, if you want, due to floor heating, you will enhance convection effect, because when you heat air at low level, what will happen is, as we studied in chapter 2, due to convection effect, air that is at low level heated will have a decrease in density, and due to this decrease in density, we will have circulation of air upward. Okay, in this way, certain molecules of air will go up and other one will replace them, which are relatively cool. So cool air that will go down will be heated again by the floor, and this cycle will be repeated, creating convection currents in the space. Okay, So from here, the importance of floor heating. The floor heating concept is very simple. What we do, we install ducts under the floor, and in these ducts, water will circulate. And due to circulation of hot water that is heated by the solar collectors, then when circulating under the floor, they will heat the floor, and therefore they will heat air that will be circulated into the space, maintaining a comfortable temperature inside my space. Now, there are seasonal variations in the energy collected by solar collector systems, because the solar energy collected depend on several factors. First, you have the location of the collector, its efficiency, the orientation of the collector. The orientation will affect a lot. So this is why it's very important to have a tracking system. As your friends presented today, when you use an appropriate tracking system, you can benefit to the maximum from the solar energy, and this will help you into ensuring higher demands for your space. So all of these effects, all of these parameters will affect the energy collected from the sun. Now, the energy can range from 0.6 to 1 kilowatt hour per meter square per day in winter, and to about 2.4 kilowatt hour per meter square per day in summer. Of course, in summer, the energy will be higher. Now, it is easy to get nearly 50% of hot water energy from the sun. So as you can see, the solar energy will provide a high proportion of the energy needed by your house. This is why solar energy is widely used in the world, especially for domestic hot water applications. These systems are easily integrated into current hot water systems and have a payback period in the range of 10 years. So currently, we are not using only solar energy, but we can implement it with other systems. But with the development and research, we are enhancing a lot the performance of solar systems in a way to reach a point where we can rely only on solar energy to provide the house demand, especially in sunny regions. Now, when you want to do the sizing of a solar water heater, when you want to decide what size I need, you need to look at several factors. First, you need to know the location of your house. So you need to know in this location, what is the solar fraction I am getting, which represents the amount of energy provided by the solar technology divided by the total energy that I need. Furthermore, you should look at different factors. So it depends on the house. So if you need to look at the number of occupants, because higher the number of occupants, higher the needs for hot water. Of course, also the behavior of the occupant. If you have, let's say, a region where you have almost all the time sunny seasons, okay, then you need to have maybe several baths per day, not just one shower. So this will increase the need for hot water. You should also look at the equipment efficiency. What are the equipment you are using? What are their efficiency? What is the temperature you want to heat to? And if you want to heat, let's say, to 45, 50 degrees, it's different than to heat to 60, 70 degrees. And as we said, especially in developed countries, due to we for safety factors, we heat a lot to kill bacteria, etc. Because at very high temperature, all bacteria can be killed, so it will be more safe for the bath. And another issue is the consumption per occupant. Okay, so nearly you need 40 liters per occupant per day, which is a standard for a dwelling.